Okay, so should we start? We'll start the second day of the Polyca Summer Workshop with Ami.
Yes, thank you. Okay, so just as a starter, first of all, it's great to be here. I mean, we should agree on that. Beautiful scenery and great hospitality. People to talk to, that's wonderful. So, what I will do today, so I wanted to talk about the guess of and Higgs punch into the which in short will be like that. But before going here, I would like to say some general words about hyperkiller cones, because it's not clear that we all know about this. I want to set up the stage for discussions on those cones, and then we'll specialize to cases where these hyperkiller cones become relevant to study physics of issues. So, hyperkiller cone, these are singularities. In some dimension, which we will call D. This is going to be the quaternionic dimension. And there is a question of how to think about such spaces. They do show up in H-theory. And I will just make a partial list. Possibly, I mean, they also show up in string theory in many occasions. And again, one can try and provide a partial list. They are all over the place, and therefore it's important to have a generic thinking about such singularities. They show up as Higgs branches. In dimensions 3 up to 6, and in this case, what we'll say is that we solve hyperkiller quotient, or F in the equation. They show up as a Coulomb branch. In 3 dimensions, n equals to 4. Here, Higgs functions of theories with principal charges. And in the treatment that we are going to use, it's convenient to set all of the parameters to 0. So masses, variables, terms are set to 0, and that's why we get the cone. Right? I mean, the cone is not. This condition is broken once you return some parameters, the information parameters. So it's in this sense it's different than what we had yesterday. Yesterday the assumption was that those Higgs functions have resolution parameters, and today we will just set that to 0. It's just more complicated. When you set the parameters to 0, you get an opportunity to treat the singularities in a very generic way. Now, let's just see some examples. So, in general, if we could have some classification of such singularities, it would be great. However, this turns out to be a too difficult problem. And so we have to find some less ambitious questions to ask. So, so to think about classification, we need to pick some order parameters. And one natural order parameter is the dimension. So I will start with the dimension 1. And here there is a classification. Those go under the name of Klein or Duval. They take the form of an orbifold. And gamma is a discrete subgroup of the C2. There is an AD classification. And this is well known. We've seen this many times in many string backgrounds. It's actually quite nice that there is a classification, and we can study string backgrounds in this way. Do I need to go over the details here, or we're okay with that?
Remind me how the elements of SU2 act on the C2? Is it just as
there is a
being in the what's that?
It's defining matrices.
Defining matrices. Okay.
so you just pick 2 points, C1, C2, and you act by 2 by 2 matrix.
Yeah. That's
Pick the 2 by 2 matrix. And it's just a representation of this discrete group. And if this representation is abelian, then we have the A case, and the T and E cases are especially non-abelian types. Let's just further look at these cases. And we will talk about isometries. So D and E have none, and A has a U1 isometry. Let me put an index and take n greater than 1.
So this is about Kerr or something. Yes.
Yes, yes. And A1 has an SC2. And again, do I need to delve on these things? I mean, it's quite crucial that there is this evolution of isometries. Nothing here, 1 here, and SC2.
Yeah, maybe you do spend a few minutes on that. That's sense.
Okay.
Yeah, maybe there are 3 experts.
So, so let's look at the final equations. And we will start with the A type. So I have 3 variables, x, y, and z. And in fact, we can even be more explicit. We can just use those coordinates. Z1 is the same as omega Z1. Z2 is identified with omega -1. Z2 and omega to the n. I didn't specify here, so let's just take omega to the n is 1. I did specify it over here,
so isn't that omega to the
so I
n?
have to put 10 plus 1. So, what did you say?
Just that.
That's really So then the equation will take this form, x, y equals z to the n plus 1. And in terms of those coordinates, we can have a very simple match that x is equal to z1 to the n plus 1, y is 2 to the n plus 1, three invariants under this orbifold action. And these three invariants satisfy this obvious relation over here. And so now we can forget about this parameterization and just think about a single complex equation in three complex variables. This is the singularity, C2 mod Cn. And there is now, we can now talk about this isometry. So, in order to introduce this isometry, we will make a slight digression and discuss the notion of holomorphic functions. So, since this is hyperkähler, I have three complex structures which are rotated by SU2, which we think of it as SU2R, this is a R symmetry that acts on supermultiplets, and it just rotates the three complex structures. They transform in the three-dimensional representation of this SU2R. Okay? Next thing that we do is we pick one complex structure. And once we do that, we have two things. First, there is the notion of a holomorphic function. Right, so I can think about all possible holomorphic functions with respect to this choice of a complex structure. But also from the gauge theory perspective, this holomorphic function is also related to a chiral operator. And the set of such operators form a ring. So this is the ring of chiral operators which have one-to-one correspondence with holomorphic functions on the modular space. So examples are these x, y, and z. These are three holomorphic functions, and they satisfy such a relation. This is the defining relation of the chiral. Okay. Now let's relate to isometries. So we will use the following theorem, which is you could think of it from supersymmetry, and you could also think of it from geometry. So all chiral operators of spin under SU2R are in the joint representation of the isometry. And this isometry, from the point of view of the gauge theory, we should think of it as the global system. So how do we go and show such a theorem? We
Sorry, all chiral operators of spin one. Yes.
sorry. Thank you. Under SU2R are in the joint representation of the isometry. We could go in both ways, both directions, show that the joint representation must have spin 1. This follows from the fact that if I look physically at the conserved current, which couples to a global symmetry, then it includes a chiral operator, and a quick computation shows that it has spin 1 under SU2R. And also the opposite way goes. If you have two two spin one objects, and you try to pair them together, you find that they generate a third one, which is also of spin one, and this forms a Lie algebra. And so there must be some joint representation of a certain group, which we then physically call it the global symmetry. So, what this theorem tells us,
Is it clearly simple?
it could be a product of many groups. There could be different ones, as usual in cases.
But I mean, not like that, like Poker, I mean, down, as you write down Poker, like semi-direct product with some.
Oh, I see.
Some-
Not that I know, haven't seen such cases, but from this theorem, they really form a Lie algebra. There is a symplectic form, and
Exactly, if there is an invariant bilinear, an invariant, if there is in addition an invariant,
The symplectic form.
invertible bilinear form.
That's right. There's a symplectic form, and you use this in order to go in this direction. That pairing, so this invariant bilinear form, you pair two of these in one operator, you get a third one, which is also in one, and this also in one. So, this is a point which is known to mathematicians, at least to Constant, if not before that. And in the physics community, I started seeing it fairly recently. It wasn't so clear up to maybe 10 years ago. You wouldn't hear talks where people would say such things. Now, what can we do with such a thing? This is really powerful, and we are just using it all over the place. So, for example, if you look at computations of indices in 5 dimensions, the way they find global symmetries is by just using this thing. It's really used, if you make a survey on papers which are recent, this is really a major thing. Also, Jacques was telling us about theories with two stress tensor operators, and he's using the same techniques. In this case, he's not looking at spin one object, but at spin two objects. And Phil actually reminded me yesterday that this is what happened. Okay, so now let's apply this to our case over here.
Can I ask a question before? So the way you presented it is as a complex space. But there might be a family of hypercare metrics. For example, on these such spaces, there is a family of hypercare metrics.
There's what?
There's a family of hypercare
Yes.
metrics. And you're choosing a very particular one. For example, to get the enhancement of SU2, you need to choose a very particular hypercare metric. Namely the infinite coupling one.
I'm not sure there is a choice here. I don't see where the choice is made.
It's the gauge coupling. For example, if you think of...
This is
Well,
just...
so far we haven't written down the next two.
Yeah.
Let alone the family there.
I know, but I'm just saying,
No, I
for
understand.
example, to see these symmetry enhancements, you need to choose...
No,
a
I
particular
understand.
metric.
I'm not disagreeing with that. I'm just saying that the question, like,
Yeah,
I
it's-
suppose when you actually start to write down the metric. But
I asked it because it seems that we're moving away from the metric.
So you're saying that there's more than one hypercalar metric?
Yeah.
That makes this a cone without homomorphism?
No, it's only going to be a cone in a very particular minute.
Okay.
So, in this case, we could just use this equation. We could actually use these relations to first determine that Z1 and Z2 have spin 1/2 under C2R. And the holomorphic function is just the highest weight of the SU2R representation. So if I take such a product, it will have spin n plus 1 over 2. This one will also have n plus 1 over 2. And this one will have spin 1. Okay? And we see that when we plug these spin assignments into these equations, they are consistent with this scaling. And besides that, we find that there is precisely one operator of spin 1. Right? Any other operator will have spin higher than that. It will just be a product. Right? So if I take powers of z to the n or z to the k, will have spin k under SU2R. But now I can just use this and realize that I have precisely one operator of spin 1, meaning that the adjoint representation is of dimension 1, giving me just U1. So I verified this point. There is one exception. If I set n equals to 1, then I get 3 objects of spin 1. They will again transform in an adjoint representation, and there's only one such tool, SU2.
Sorry, could you repeat this? Sorry for being slow. That didn't sound like very important.
Spin 1, only one operator, which is Z, right? And therefore, the isometry is U. Right? And the only exception is that n equals to 1. I have 2 more. Right? At n equals to 1, only x and y have spin 1, and now they form an adjoint representation for the C2.
So
Here I have
3.
3.
Yes. So without using your powerful theorem, you could just say, what is the subgroup of SU2? It's an algebra that commutes with your choice of U1 or SU2.
Yes, certainly, certainly. So this is another way of verifying that this is the case. And indeed, if I take n equals to 1, then omega squared is equal to 1, so it's just minus 1. The action actually has an SO4 isometry, which divides into 2 SU2s. One is SU2R, and the other one is SU2, which acts on the SU2. Okay. So now, what
so still you have a SU2R symmetry, right?
always.
Always, right. So
All these hypercalifores will always have at least an SU2R.
and then this isometry is additional isometry.
What is it? You
Yeah,
say hypercalar SU2R.
Oh, okay.
Okay, and there could be additional structure on top of it.
Yeah, the lower symmetry.
The SU2R is not an isometry.
It's not isometry, it's just.
It rotates the complex structure.
Oh, okay.
Yes. There was a comment for you. Say, right. Yeah, a comment on so whenever we deal with orbifolds, we have an explicit construction. But if we don't have orbifolds, we will have to become more general, and there this thing will be very crucial. So here we're kind of lucky, or maybe unlucky, in the sense that there are very few explicit constructions, and whenever you have an explicit construction, you could use other techniques to verify certain statements. Okay. On the other hand, if you look at the D and E cases, you could again, write down the defining equation. It's not that hard. So let me write for you the defining equation for Dn. We'll have x squared plus y squared times z plus z to the n minus 1 equals to 0. This is the defining equation. And now if you try to fit the spin of SU2R, either by picking some gauge theory construction or some other way of just explicitly verifying the orbifold itself, you will find that the Z, which has spin 1, in the A-type case now has spin 2, and there is no operator of spin 1, and therefore we conclude that there is no additional isometry. The isometry is none. The same thing goes for E-type isometry. Okay, so are we okay with this survey of the D equals 1 cases? Now, let me just emphasize that this appearance of SU2, this case D, calls for a new way of thinking about hyperkähler codes. And now we could ask the question about hyperkähler cones.
Sorry, maybe it's a very silly remark or question, or you have told that. But we can already see at the equation and try to identify isometries of that equation.
Yes, that's it.
Is that the correct picture? Or?
That, again, the comment that I gave to Philip is relevant, that this is a case where we have an explicit construction. And if we don't, then we'll have to be more clever than this. Yeah.
Kind of the converse, though, is if you go to higher dimensional orbifolds,
yes,
you know that generally this chiral ring can become very complicated.
Right.
The number of generators and relations goes up, so
yes,
it may be that you're in a difficult situation generically also in terms of chiral.
And so thinking of orbifolds will not prove to be a too fruitful direction. I mean, you'll have to work hard. You don't like to work hard. So you have to be more clever. Okay, so here's the point. Here is we could now just try to think what is the set of hyperkähler singularities which have an isometry. We will exclude cases like the D and E cases. We will get some nice class of theories. And what it means is that we pretty much need to look for spaces where if we know how to compute the sweet P1 operators, they will transform in some adjoint representation. So let's do again examples. In D equals to 2, and ask what kind of spaces can we get which are singular. And of course, we could just take an ALE space times another ALE space. That's an obvious thing. And as a result, we could have cases where there's only none or U1 or U1 plus U1. U1 plus SU2 or SU2 plus SU2. I hope that if you find that there is something.
Yeah, just SU2.
Just SU2. Thank you. Right. So and again, it's quite clear. The node will be a product of D and E with the D and E. The one will have one component which is A, and so on. Right. So we could have those different cases, but we will also have two additional cases with an SU3 and with an SP2. Those are my spaces. The SP2 one is again again an orbifold. It so happens to be an orbifold, C4 modeled out by Z2, where the Z2 acts by reversing all signs. It is a complex space, but you could also think of it as a hyperkähler modularized space where the isometry is sp2. I mean, in general, what you just do is you take, this is a 8 three-dimensional space, the orbifold commutes with the action of SO8. So this space will have SO8 that you pick an SU2R, and the commutant of this SU2R is just SU2. Okay, so this becomes the isometry of this model space. SU3, we heard about this space yesterday in a few occasions, and I will write this space in a way which we didn't write so far. Actually, I hope that people will use the type of notation that I'm using now. Hasn't been used so intensively, and it's about time that we will start using it. We do know about this space for a long time, and I just write it as the space of 3 by 3 matrices with complex entries, such that m squared is equal to 0. Simple space, and this m squared, you should think of it as a matrix condition. As a challenge, you could try and convince yourself that it has a complex dimension 4 or whatever like 2, and that it has an SU3 isometry. Okay? Alternatively, you could replace this condition by the condition of the rank, that the rank is at most 1. Those two, I mean, I can either write it as the space of 3 by 3 matrices with 0 square, or the space of 3 by 3 matrices which have rank at most 1. And there is a more physical way that we are familiar with this space. This would be the space of the reduced one instanton modular space of SU3. Right? So if I just think about a single instanton in the range of SU3, and I ask for the set of all possible solutions to the self-dual unit equation, I will find that the description is given by this set of equations. So this is more familiar. We've been playing with such moduli spaces for several decades. However, very rarely you would find such a description of a moduli space. So that's why I'm hoping that this will change. Questions?
So you have a product of these, like, say C4 by Zn times Zn, where they both act as a four-dimension.
So you could have it in this context like that, where you act separately on one pair and another on another.
No, that's I understand. But suppose you have a product which acts on both.
Then you will have a hard time in, maybe not so hard. You have to figure out whether this preserves the hyperkähler structure or not. I don't have an easy way to do that. You could try to see whether you could construct it as a hyperkähler quotient, or a Coulomb bunch of some theory. But a priori, yeah, if you pick a generic overproduction, we will need to think whether there is an SU2 actually. Do you want to say?
Can I ask if someone just hands you a chiral grid
Yeah.
without anything else, how do you know, is there a way to test whether it arises from a hyperkähler cone?
Excellent question. It's there's been some progress in the work by Namikawa, which you may have looked at, and there's also this notion of synthetic singularity by Bourvil. And so their work provides you some criteria to check whether the model space is hyperpedal or not. I might touch the Namikawa thing. I mean, the Bourvil is fairly technical, so I'm not sure if we will help, but this is really an excellent question. More questions, Philip?
Yeah, so are there examples of two-dimensional cones that, like the ALE cross ALE case, have not just isolated singularities, but codimension 1 lines of singularities, but that are not in the ALE, that are not a direct product?
I'm not sure how to formulate this question. Yeah, I understand the question, but you will have to think how to formulate it to fit this type of question over here.
I'm not so concerned with the question of the existence of isometries, but just whether there are any examples of such two-dimensional cones.
Yeah, I'm not sure.
They actually arise if you try to ask questions about two-dimensional Coulomb branches. Let's say in the 3D context, or actually put them in the 4D context.
So, yeah, so let me present some general description, and then we can try to think about these general descriptions. So, we could have the class of all gauge theories. So by saying this, I assume existence of a Lagrangian with the gauge group G. This is the gauge group of rank 2. So we pick the rank to be equal to 2 and introduce all possible methods. So this is a very large class. You could just pick an random selection of representations that are coupled to this gauge group. There are only 6 groups which have rank 2, so we could just classify them. There's a U1 equals to 1. There's a U1 times C2. And all the rest are A2, D2. And again, I think I forgot 1.
G2.
And G2, thank you.
D2.
That's the one. Huh? G2, D2 is
SU2 process, yeah.
So those are the 6. And so now you could just add matter as you wish to these groups. The existence of a U1. So these are 3D theories. Maybe I should put here. Maybe N equals to 4. Gauge theories. So this gives you a very large class of hyperfilar cones of dimension 2. And I was hoping at some point that one can classify those, but it turns out that this is too hard again. You can use atomic geometry in order to make some order in this class of theories. Maybe I should mention the work that we did in Schrodinger's. If you want to see some details, there are 2 papers with Marcus trying to address this issue. And so now you could just look, pick your favorite gauge to it. You pick your, so one of those 6 gauge groups, pick any matter content. Increasing the matter content will change the type of the singularity. It will be bigger and bigger singularity. Roughly, it's going to be the index, the analog of the index, dn, an for the one-dimensional case, and try to get a set of such singularities. Apparently, it's too hard, but it's still a nice lab for testing various ideas. So it's
I just point out that, of course, you can also get hyperkähler cones from 4D n equals 2 Coulomb branches, because the total space over them has a natural hyperkähler structure. And there's many examples, for instance, in the work of Jacques and collaborators and some earlier work, that don't obviously kind of flow to these to 3D examples.
yes, but
They're cones if you take them conformal fluids in 4D. And then
the codes you said.
What?
I mean, my understanding is that if you are in 4 dimensions, and let's say you put it on a radius, on a circle of some radius, then you lose the control.
This is the natural hyperkähler structure kind of corresponds to the limit in which the radius of the circle is infinite, and so you retrieve it. You don't break the.
But then you're back to a 3D field.
No, the radius is infinite. It's not a 3D. It's kind of a UV.
It would be nice actually to look at those cases and see how they fit.
Or at least there's not a branch in 3D theory.
Right.
We should be
Yes.
more cautious about that.
Yeah.
Right. Okay. So.
So now it's a basic question.
Yes.
So what was the statement that you made in that box? Like, here's the class of all 3 equals to 4 theories?
It's a class. It's a class of 2-dimensional, which it's a construction, if you wish, of 2-dimensional hyperkähler cones.
Solve the F and D term equations with this.
Not the
The Coulomb branches.
The Coulomb branch follows theory.
Coulomb branch follows.
Usually I'm talking about the Higgs branch.
No, this
Coulomb
is the Coulomb branch.
Okay, so it's very different.
It's very hard. If I give you a hyperkähler quotient, you have to compute the dimension of the model space. You just need to count how many vectors, how many hypers.
That was my question. The Coulomb.
The Coulomb, yeah.
Well, that's one.
Coulomb is a hyperkähler of dimension.
So, you said that you can add any methods, which you give you for
Yes.
not complicated singularities. So what's the problem with classification? Or you can interpret
so you'll have to think about, so the Coulomb branch is the space of dressed monopole operators. And the more matter you add, the more complicated the equation for the scaling dimension of the monopole operator becomes.
okay.
And this scaling dimension contains absolute values. And those absolute values generate wedges in the space of magnetic charges. In each of such wedge, there is an analytic behavior of the formula for the scaling dimension. If you move to a different wedge, you get to a new analytic behavior. Now, what is the problem? The more matter you add, the more wedges you construct. So you should imagine the space of all possible magnetic operators. It's not a big deal because it's just a 2-dimensional space, right? So it's just a set of, it's a lattice, 2-dimensional lattice, GNO charges, and it's just divided into more and more wedges, and it doesn't stop. The more matter you add, the more wedges you get, and the description becomes more and more complicated.
So singularity becomes more complicated.
And the singularity becomes more difficult. The ring, the chiral ring gets more generators, and I'll have to provide more relations. It just becomes uncontrollable, at least not in the way that I found how to deal with it.
So,
It's a nice problem.
right, so that's the A2 case. SU3
Yes.
is just fundamental matter. That's doable. If we have a lot
SU3 with fundamental matter is
lot more fundamental
trivial from this point of view. Yes. Now add the 2-1 representation. So this young diagram adds as many copies as you wish. Take this representation. Take this one. And so on. Just pick as many copies as the more you grow with the size of the representation, the more wedges you construct on the GNO lattice, and the computations become difficult. Okay. So it's a nice exercise. Actually, if you look at the techniques here of those geometry, quite nice. More questions? Okay, so now what we're going to do is to, where's the eraser? What we're going to do is to think more of hyperkähler cones with an isometry and try to make some general statements. And in order to do this, we will just set a new order parameter. So our first order parameter was the dimension, and we gave 2 examples for t equals 1 and 2. And our new order parameter will be the representation under SC2. And in order to present this order parameter, we're going to think of a chiral ring. And this chiral ring is finitely generated. It's a finite dimensional space, and therefore there are finitely many operators in the chiral ring which generate the whole ring. And so denote the R symmetry of the representation under SC2R by RR, right? A collection of highest weights under SC2R with quantum spins. And this is a finite set. Okay. So let's try to see what can we say about this finite set. Suppose that some Ri are 1/2. Okay? So I have a generator of the ring of spin 1/2. Actually, you could convince yourself very quickly that there is an even number of them. So 2m such for a certain choice of m. And in this case, the moduli space contains a simple factor. It's a trivial hyperkähler moduli space. Jacques likes to call it HM. Right?
Okay.
Yes.
I suppose I would like that.
So physically what it means is that we have a gauge theory, field theory, in 3 dimensions where there is a free sector and this 1/2 is the totality bound. We have a collection of gauge invariant operators which have spin 1/2, and so this generates a free sector. And so we could just ignore this free sector. Right? So from this point we can assume that Ri are at least 1. Okay. So this will be an interacting sector. And we just made the point that if some of the Ri are in Algerian representation, spin 1, then they are in Algerian representation. So I'm going to suppose that all Ri are 1. Okay? Which means that I have a modular space where all generators of the chiral ring have spin 1 and no other generators. And here, again, there is a theorem over here. The modular space is a closure of the loop operator. Which is the first time I mentioned this name in this meeting. The nice thing about such a statement is that there's a classification of all of this. That's it. You just need to know what are all possible limit orbits. And there we go.
You already gave one example, right?
Yes, right. We saw one, which is erased already. And we saw actually 2 and 3. So, yes.
So, who's Hill, or what's Hill's first name?
Sorry?
You said you ascribed this result to Hill?
No, I may have been misheard.
Oh, sorry.
This is
theorem is-
Namikawa.
Oh, this is Namikawa.
And is it no person orbit in what? ADEs, is that right?
They put the orbits on what?
In what?
You mean the field? Or what do you mean?
What's the algebra?
Any algebra.
And not just say ADE.
You just need to figure out. No, it's not. You just need to figure out what adjoint representation those Ri for. Right? So let me be explicit about it. We put an orbit of an algebra that is generated by the spin 1
It's not just any of the algebra, it's reductive.
It's the assumption, no?
It could be reductively algebra and
That is to say, it has an invertible invariant.
Yeah, so that's related to this question. From the cases that I've seen, the algebras are fairly vague. see how far we can push this the assumption on the algebra. But what I have in mind at the moment is just that, you know, a pically algebra doesn't have to be simply based. It could be containing a collection of U1s, product of non-abelian factors, and the normalized space would be a nice normalized space. We could also come up with some gauge theoretical construction of this normalized space, either as a Higgs branch of some theory or Coulomb branch of theory, or a Higgs branch at infinite coupling of some phi. Okay, but what is the power of this thing? It tells us that all moduli spaces, all hyperkähler codes which have an isometry, must start with an nilpotent orbit. Okay? Nilpotent orbits are basic. They form the skeleton, the basis of all possible hyperkähler codes. Right? Any code with isometry is an extension of a closure of an nilpotent.
What does the word extension mean in that?
So we should think of it in the form of chiral ring. Right? So we have
So you have a projection to the RI.
by setting
all the others
all
to
the others
zero.
to zero.
Okay, so it projects to a nilpotent orbit.
Maybe a projection.
Yeah.
But there are plenty of clans with no isometry, so there's huge number of
And for them we will not know what to say. It will be, it's still correct, because there is always a trivial orbit.
Good.
And it's not an equation.
Sorry, could you then just for everyone summarize what the extension is? Basically, just
So the way Jacques, let's see how Jacques.
So take all of your generators with the chiral ring and map all the ones with spin greater than 1 to 0.
Oh, I see.
And the remaining ones map to a closure.
Oh, I see. I see. So extension in that sense.
So it's a projection, projects to a nilpotent orbit.
Excellent.
And let me say something which is clear. I'm not saying difficult statements. It's all
So you could also say in the same way that everything is an extension of the free one. If you set all the ones different from one.
Let me say it in this way. Whenever you have a moduli space with a global symmetry or gauge theory, look for the nilpotent orbit. Right? There will be some subsector of the system still interacting, which will form an nilpotent orbit. So it will be a nice subsector of the theory. And that's the thing which is certainly new in the physics community. I think that we can extract a lot of physics from this segment. Yes. What does this mean now?
Wait, coffee break.
It's a good time. Okay. We will start now by trying to think about five-dimensional gauge tools. We will slowly make our way towards five-dimensional gauge tools. We made some bit of preparation with understanding symplectic singularities or hyperkähler codes. And at this point, what I'd like to do is to give some examples of moduli spaces which are of higher dimension and are within this class. So let's do simple things like an 8 theory it will look like a linking diagram of the 8. So here's the linking diagram. And what I should think of it is as a gauge group, where every node is a gauge group, UN. And there is node 1, which is the tuple. This is because all edges are connected to nodes, so if you work it out, you'll find that there is a U1 gauge group for which no field is charged under. So I'm free to pick which U1 to ungauge. So I can ungauge any of these. I could do this is a natural choice. Or I can ungauge the U1 which is inside this U6. There are several natural choices. But the statement about this is that the 3D Coulomb branch of this theory is the closure of the minimal orbit of the 8, and I will multiply this. Right? That's the closure of the nilpotent orbit, the minimal nilpotent orbit of 8. Okay? Tell me if you need some more details. I could provide more details, but I prefer to. For E7, there will be a very similar construction. We will have this, and we've been knowing these quivers for several decades now. We played with them quite a bit. And it's fairly well known. I'm going to use them, and that's why I mentioned them. So this is an example of the hypercare cone with an isometry E8, isometry E7. It's quite a high dimensional model space. For example, the space here will have dimension 29. Here, the space has dimension 17. And for the case of E6, I'm going to have an 11-dimensional space. And again, the Coulomb branch of this is the closure of the minimal nilpotent orbit of E6. Okay? So that's a nice thing. And what we could now promote as a general principle is that to construct hyperkähler singularities hyperkähler cones, I have two ways. Let's go back to the statement we said at the beginning. I can do hyperkähler quotient. That's the origin of the name, which is just to write down a set of F and Itten relations for a certain VHD. Right? These guys will not have it. I don't have a simple construction as a hyperkähler cone or as a hyperkähler quotient of those three spaces. In fact, the simplest construction is through thinking of them as a 3D Coulomb branch. So that's the first point. The second point is as a Coulomb branch. Of a certain field. And when when I say a Coulomb branch of a certain quiver, the information that I need to provide is just a collection of numbers which are connected by some graph, right? So the whole information of this hyperkähler singularity is just encoded in the choice of the diagram and in the choice of the numbers that come associated with it. For example, I could have changed the numbers here to be different. My gauge groups are going to be different. The cone will be a different cone, but here's the data that I need to provide in order to compute the properties of this cone. Right? So once I'm given this graph, I've done the work of characterizing the geometric properties of these moduli spaces. So now, instead of getting into the technical details of how to construct these moduli spaces, I'm just going to say, okay, this is the information I'm going to provide. Given a quiver, I could apply a collection of techniques, gauge theoretical techniques, in order to figure out what are the properties of these moduli spaces. But once I pick those numbers, I'm done. The rest is just technical details. So this is the approach that we're going to take now. We're going to play with such diagrams. It's much easier to play with diagrams than to actually compute the properties. The metric, if I can, the algebraic variety, possibly the generators of the relations that they satisfy. All of these are very important questions and could be a topic of several lectures. But at the moment, what we will do is to just concentrate on getting such quiver fields.
But,
yes?
So these are just some specially chosen quivers, but they don't have, there's just any general quiver will define in principle.
Right. Yeah. So now what is special about those quivers, which we have to figure out from those numbers? This choice of numbers is not an accident. All of these quivers are nilpotent orbits. What does this mean? The generators of the chiral ring are all of spin 1 under SU2R. So it's not that random. Right? It's a very particular choice. And I'm going to pick my quivers now very carefully, such that they will be very either nilpotent orbits or very close to the ones. Okay? So this is the, if you want, it's the next set of points that we are trying to study. We study hyperkähler cones with an isometry, and we reach the conclusion that the basis for all of these are closures of nilpotent orbits. And now we ask the question, suppose that I modify it by a bit, a little bit, slightly more. What kind of moduli space do I get? Right? So those are the moduli spaces which are almost nilpotent orbits, where the notion of almost is still, I'm not sure I can give you a clear notion of what it is, but we will try to explore this direction. Any questions?
So the fact that all the nodes are balanced
Is the next point, yes, of course.
Right, so how does that translate to the geometry?
Okay.
The intersection of the resort with something?
Okay, so here's the next theorem. Given a quiver with a unitary with a set de facto, the subset of a balanced nodes forms the Dinky diagram this is
The affine. The affine thinking diagram of the.
no, it's the final. In this case, to match with those squiggles, what you need to do is to pick U1 that you engage or just decouple. So for convenience, in this case, just pick this one. And then the remaining set are balanced nodes. And they form a linking diagram of a finite dimensional linear algebra that is over the distance. Well, the balance of the node is the sum of neighbors and minus twice the node. Actually, if it's non-zero, I will call it the imbalance. If it is zero, it's a balanced node. If it's non-zero, it's an imbalance. Okay, so let's say.
So this is, you're of course only capturing the semi-simple part of the global situation.
Yes,
Your scale.
that's right.
So all the U1s that you talked about.
Just match with the
What?
It's very simple. It's just match. So the number of the ones
Right.
is the number of unbalanced nodes. The minus one is because of the.
Yeah, because they don't drop.
Yeah, that's so. And here is an important point to mention about three-dimensional gauge theories. Whenever I have a U1 gauge symmetry, there is a corresponding topological U1 global symmetry, which contributes to the rank of the Fourier symmetry. Okay, these are well-known things. If you want me to go over this, I'll be happy to do that. Otherwise, I'll just. Okay. Questions?
What happens if you double the rank for each node?
Then you get a nice normalized space. It's no longer an important orbit. It has twice the dimensions for sure. And in this particular case, it's going to be related in some simple way to the normalized space of 2 instantons of the which is not an important topic. There are generators of spin 3/2 under the SC2R symmetry. So it's not something I would like to develop now, because it doesn't serve the purpose of thinking about 5-dimensional. Okay? So I want to take a different route. I want to not to double ranks. Double ranks is kind of it's a violent action on moduli spaces. It doubles the dimension without gaining much of the isometry. I want to change it by a slight amount to get the quiver which is slightly different, slightly unbalanced, except that it's a minimal cost. Right? So how do I do such a thing? So let's try to develop something like that. And let's take the E8 guy and take a maximum subgroup of 16, like this. And with this maximal subgroup, I can see this maximal subgroup. It's over here, right? It's this part of the window. And what I want to do is to preserve this part, to keep it balanced, and to make only one node unbalanced. minimally unbalanced quiver. What is a minimally unbalanced quiver?
May I ask a very, very dumb question? Could you, so should I take this imbalance as the sum of the neighbors?
Yes, yes. So,
Let's say,
for 4, I have 2 neighbors.
yes, so that is 8.
8 minus twice the
I see. Perfect.
is 0. So
Okay.
that's a balanced node.
Excellent.
Right? And now I'm going to slightly modify it. And I'm going to do it in such a way that I will have a generalization, and I'm going to pick something which we will understand later. I'm going to change this SO16 to SO4n plus 8. So the case n equals to 2 fits with this case. And so now what it tells me is that I have a 2n plus 4 balanced nodes. And 1 unbalanced. Okay? And I want to construct such a quiver. And from these descriptions, because I picked SO16, the one which is a candidate for being unbalanced is the one which is connected to the spinor representation of SO16. So that's going to have some consequence. I'm going to write down the following quiver, and it's a single choice. There's not much choice. 1, 2 goes all the way to 2n plus 1, 2n plus 2. Right, so I have the first 12 plus 2 nodes are all balanced. In order to make the spinor node balanced, I put n plus 1 over here. If I add up those things and I want to make it balanced, it should be n plus 2. And to make this balanced, I must put the 2. Here's my quiver. For the choice that n is equal to 2, I'm going to get this one. And I get an accidental enhancement of the symmetry from SO16 to 8. So if I look at this class, it's a 1-parameter family of quivers, has an SO4n plus 8 isometry, and it has only 1 unbalanced node. What's the imbalance of this node? So the imbalance, the number of neighbors, so it is only 1 neighbor, n plus 2, minus twice the node, minus 4, that's n minus 2. Okay? Whenever I have such an imbalance, it tells me an information about the generator of the chiral ring. So this implies a generator in the chiral ring of spin n over 2. How do I know that? I have to discuss the physics of 3-dimensional Coulomb branches. It's by the scaling dimension. Basically, what I need to do is to find a monotone operator, which is associated with this node, and I need to show that it is carrying this representation of the residual. Okay?
Is it a simple formula, like it's the imbalance plus 2 divided by 2 for the spit?
Yes, that's precisely what it is. Yes. So I just need to add 2 and divide by 2. Yes. For n equals to 2, it will be spin 1, and anything else that will be. Actually, when you play with the formula, it's a bit long, but when you play with the formula, it beautifully fits into these simple statements that we're going to see now. So what I'm doing now is to save all of the technical details of the numbers that you put in. I just give you the final answer with a very beautiful picture.
But sorry, what happened if you choose a different subgroup from the start? Like here you said that you took this SO16.
Right. That gives us a richness in constructions of minimally unbalanced equivalence. And the hope is to fit a theory for each one of these cases. And we will see this. For E8, I don't know of another one, but for E7, I'll give you two.
So your construction here is basically theories with a simple isometry group.
Yes.
Right? That's
Which is another order parameter. Thank you very much for this question. So when we have hypercolor with isometry, we could still refine the notion of isometry to have a single factor, two non-abelian factors, one abelian, one non-abelian, three non-abelian, and so on. Right? This will be the complexity. And the more factors you'll have, the more U1s you'll have, the more complicated the model space is going to be. Right? So what I wish to have is a collection of non-abelian factors without any U1s. This will be the perfect situation, but in some cases I won't have a choice and I need to pick either one or two, and it will become more and more complicated.
Sorry, if you, for the last node, if you instead of taking two, you take other value, or even the value that would make...
then it will make this unbalanced. Right? You see?
Yes.
That's the only choice for making this value. So, you know, I didn't have a choice. I started with the long leg. I had to increase by one. Right? So the minimality. That's the question. I could have taken 2, 4, 6. That's not minimal. So I just balance this leg. When I come here, I don't have a choice. And so on. I mean, what I'm doing really here is to invert the corresponding pattern matrix. So I don't really have a choice. I mean, it's a unique solution.
And you have to stick, add that extra node in one of the other two extremes.
I could have done it, I mean, those are two equivalent stream representations. I could do it either here or here, it's the same thing.
And the other doesn't also.
Here?
On the left.
Yeah, what about this?
Well, you don't do it because you cannot keep one part.
One is part,
Exactly.
one neighbor which is 2.
Yes. Exactly. You cannot add anything.
I cannot add anything to it. I will make it unbalanced and then I lose this global symbol. So there is a unique choice. If I want a single gauge symmetry and an unbalanced, minimally unbalanced, then that's it. And that's the thing. Well, I should also, I have another degree of freedom. I could pick the unbalanced node to touch a different node. It could be any of the antisymmetric representations. Doing it on the other spinor would be equivalent. I can put it over here and you'll have equivalents. They will, in this case, won't lead to interesting cases. That's the only one which is interesting. But of course, we have to check it.
Question that last statement. So, when you compute the charge removal operator, I mean, you basically compute the charge of a U1 that is preserved by the removal operator. And you're actually saying that n over 2 is corresponds to a representation of SU2R, of which the U1 is a subscript. So there's a choice of the subalgebra that you break. So how is that?
Which subalgebra?
So you initially had it equals to 4. When you have a monopole operator, you break the supersymmetry, half the supersymmetry, it's half BPS. So what you compute as a monopole charge is the U1 charge of whatever is preserved.
Yes.
Correct. And here you have, you're labeling it by representations of SU2R as opposed to U1R.
Yes.
So
I'm still n equals 4 supersymmetry. I did not break to n equals 2. So I should be more careful about assertions before. No, I did not break n equals 4.
So then how does the monopole formula factor in? That's my question. When I think of monopole formula, I always think of U1.
It's going to be a function of all of the magnetic charges.
Yes, that's exactly the point. When you have a magnetic charge, you break half of the supersymmetry. So it's
It's a
essentially.
BPS state. I'm still having n equals 4 supersymmetry. I mean, it's not different than the case of balance or any of the other cases that I discussed before. It's still n equals 4 supersymmetry. When you say breaking half the supersymmetry, I refer to BPS states. Yes, of course, we break half the supersymmetry. Still keep n equals 4
It's
supersymmetry.
just that those monopoles will fill that.
It's a short representation. Here, nothing difficult here. I'm following the standard procedures, nothing really fancy. And you know, my analysis here is as good as the analysis for U1 with n variables. If you have a question, you should ask it. And I just generalize the techniques. I don't do anything different. We can discuss it. More questions? Okay, so another point that this diagram tells me is that because there is an unbalanced node in the which is touching the spinor representation, I can also determine that this generator not only transforms in spin n over 2 and residue R, but it's also in the spinor representation of the isometric group 4n plus 8. And again, to show this, I'll have to construct all of the weights of the spinor representation. And that's the part which I say it's the technical part, and I just give you the final result. So we end up with a modular space which has two generators. So two generators. The first one is a spin 1 and is in the joint representation of SO 4n plus 8. And the second one is in the spin n over 2 of SO2r and in the spin representation of the same group. It's very useful to compare with the n equals to 2 case. What happens in the n equals to 2 case? For the n equals to 2 case, both generators become spin 1. They must form an adjoint representation of a global symmetry, which is well known to be the adjoint representation of the 8. So we have an accidental D8 global symmetry. And both of these generators nicely combine into adjoint representation of E8. So E8, if you wish, is the first in the sequence. Right? There is a whole family of quiver theories, minimally unbalanced. They have a modular space which is generated by those two guys. You could also specify the relations. I will not write them down now, but it's fairly straightforward to write down relations. And this is your modular space. The dimension is just given by summing up all of these numbers and subtracting 1 over only 1, which is unchecked. So whatever the sum is the sum, this will be the dimension. And now I'm going to relate to a set of 5D theories. So here's my model space. I'm going to argue now that this is the answer to the question that I was posing at the beginning. So now take a gauge theory in 5 dimensions. It's going to be, I'm going to write it as a primal SUN gauge theory with Chern-Simons level 1/2 and number of levels is going to be 2n plus 3. So this theory was studied by several groups, and Kim Young has, with this group, has this analysis. Tell me who was the first to discover that those theories have global symmetry of this form. It could have been in one of your papers. So the claim is that the global symmetry at infinite coupling is SO for n plus 8. And this is an enhancement of the classical symmetry, which we read from the quiver. There is a Fleddle symmetry, which is 2n plus 3. That's the obvious one. And there is an additional V1 symmetry coming from the instant number. So the rank of this classical symmetry is 2n plus 4, and also the rank of this Fleddle symmetry at infinite coupling is 2n plus 4. You remember this set of rules? Yeah. So now, what I presented to you is going backwards. I started with here. I picked some generalization, which is kind of random. Maybe it's along the lines of this notion of identifying simple moduli spaces. And now I'm trying to argue that this is actually a moduli space which shows up in a gauge theory. So the Higgs branch at infinite coupling of this theory is the Coulomb branch of our class of theories. And why is that? So let's go to Pn. Coulomb branch of this. Now, why is it like that? Because I don't really have a choice. That's the only hyperkähler moduli space which has this isometry and these properties.
Question?
Yes?
Is there a direct relation between the theories, for example, by dimensional reduction and then mirror symmetry?
Yes, it is a theory of class S.
Yes. Or mirror to a theory.
It's a mirror, very good. So it's a mirror to a theory with class S.
Yes.
So if you construct the 5-brain web
Yes.
of this theory here,
Yes.
and you go down in one dimension,
Yes.
you will find the class S theory, which is mirror to this.
Great. Yes.
Okay. So it's a nice realization of this form. So here's one result. Once we state this result, we can work plenty of details about the physics of this theory. Okay? There's the 5D theory, it's very explicit here, it's given by Lagrangian. There's the 3D theory, it's also given by Lagrangian. And now we have this nice task of comparing quantities. One quantity over here, try to figure out what it is, what's the physics behind it. There's a lot of nice things to do. Instead of going along this route, let me construct another example, trying to answer your question. So, E7 has two maximal subgroups that I can think of with a single factor. There is an SU9 and there is an SO12 times SU2. Both of them satisfy my previous condition that I want the factors that do not have a U1. Okay? So I'm going to construct a family for this one and another family for this one. Okay? Then you will fit, I will fit with the global symmetries that these guys already do. Right? So how do I do this? I take the E7 theory and I look for the SU9. Where's the SU9? This is the set of 8 nodes over here. So this tells me that this is the extra node that I should make unbalanced. All the rest should be balanced. So how will I do it? This corresponds to the case n equals to 2. For the case n equals to 2, the middle node is 4. So I'm going to do this extension. 1, 2, as before. It is symmetric, as you could see, Q is symmetric, so I need to construct it in such a way. Here I'll put an n plus 2, and here I'll have n plus 1. Let's do the explicit n plus 1 over here. And it goes down as 2, and then 1. All of these nodes are balanced. To make this node balanced, I need to have n plus 1, n plus 1, and a 2. That's it. Okay? What is the global symmetry? Did I make a mistake here? Yes, I did make a mistake. It's not SU1, it's SU. Sorry for that. We should cut it. We are tired, right? There are 7 nodes here, therefore this is SU. That's rank 7. SU9 is a maximum subgroup. Okay, so here's my quiver. Here's my quiver. It's constructed in such a way that a single SU isometry factor, one unbalanced node. This unbalanced node has imbalance, which is again equal to n minus 2, except that now it's connected to the middle node. So I can generalize these statements. I have 2 generators. The first one has spin 1, meaning the joint of SU 2n plus 4. Right, I have n plus 2 nodes, n plus 1, n plus 1, so that's 2n plus 2, 2n plus 3. This is SU 2n plus 4. The second one is in the n plus 2 rank antisymmetric of this isometry group. There is a nice thing here that the role of the spin-off of a rotation group becomes the maximally antisymmetric representation of the unitary group. In the spirit of the news, today we would call it, this is the new spin-off. So you say 50 is the new 30. This is the new spin-off. Okay? So I have this class of polarized spaces. Again, very easy to write down so the generators we have, the kind of relations are also straightforward. You can write them down. You can get the very explicit description of the chiral ring. And now I need to fit it with the phi theory. So the column branch of this will be the Higgs function with coupling of a quiver that starts as an SU with Chern-Simons level 0, and the flavor group is 2U plus 2. Okay? And again, fitting this with n equals to 2, here will give me SU2 with 6 flavors, which is well known to have an E7 global symmetry. The quiver will become the E7 quiver, and for any n higher than 2, I will have this prediction. Now, if you look at the set of works on 5 dimensions, you will see that they did find that the global symmetry for these theories is SU 2n plus 4, as said over here. Okay? Let's do the next one. And it goes in the same way. Now it becomes a game. So let's look at the quiver that I have. If I pick this node, I will have a subgroup which is a D-type, and there is an SU2. That's the corresponding subalgebra. So I'm going to construct the quiver in the same way. I'll have 1, and it's going to be and n, in this case, 2n, like that, and this one will be balanced by n. Before that, let me make another one. N is 1 to n. This is n. Now we will make this balanced. We still want to make it balanced. So this should be n plus 1. This one, we don't want it to be balanced, but we do want it to have n plus 2 flavors. Well, so I want to make this balance, so this forces me to make it a 2. And in order to make the extra node balanced, this must be a 1. So this is the only node which is unbalanced. Okay? And again, as you could see, here, again, the solution is unique. I just invert the Cartan matrix. I derived it here in some way which may look as if it's ad hoc, but it's just an inversion of the big Cartan matrix. Now, sorry.
Could you have chosen instead of 1 something to make the 2 balanced?
Not really, because if
because of n. Sorry.
I wanted this to be balanced, so this fixes this.
Sure.
And I want this to be balanced and so on. This is the node, which is the only node which is unbalanced. And the imbalance is again n minus 2. And so, the statement here tells me that I have spin 1 in the adjoint of a product group. It's SO2n plus 2.
4n plus 1.
So the number of nodes is 2n plus 2, so I need to multiply by 2. Right? So this is the enhanced global symmetry. Now our friends should tell us that this is the global symmetry that they find for a 5-dimensional theory. Right? I'll tell you the global find the theory again. And the second point is that it transforms in the fundamental times spin-off the computation of this global symmetry. Okay, as you can see, for the SU2 it touches the fundamental representation, and for the rotation group it touches the spin representation. Chiral ring is explicit, and the Coulomb value of this theory is the difference between coupling of a very similar theory, except that the Chern-Simons level is 1, and the Flavor symmetry is 2U and H2. Okay? And now you can feel this is the global symmetry that you find. So now we have kind of a puzzle now, right? For every global symmetry that is found in the 5D theory, we could match a quiver along the lines of the construction that we have. So we can continue this, and we'll not do it again. But you could see the ease of constructing those quivers and getting those moving spaces. Let me make a summary. First of all, I'll summarize what's the goal in understanding 5-dimensional gauge theories. If I take a 5-dimensional gauge theory for single cases, like a single gauge group, like in those cases that we see here, something happens when the gauge coupling goes to infinite value. Instantons become massless, and there's going to be chiral operators in the chiral ring, instanton operators which will become massless, and as they become massless, they can add more directions on the Higgs sponge. The Higgs sponge becomes bigger, and it could also enhance the flavor symmetry. So both things happen. The flavor symmetry is enhanced, and the Higgs sponge becomes bigger. The dimension is larger. There's one more generator on your model space. And so our goal is to come up with the general prescription to figure out what is the Higgs sponge whenever some of those couplings go to infinity. Right? This will reveal the physics of instanton operators. They are non-perturbative operators, therefore they are very hard to analyze, and we want to get as much information as we can for such objects. And so this is a step in getting such type of information, and the surprising point is that it's quite easy to write down the answer using Coulomb branches in 3 dimensions. So that's one point. I don't know how generic is this thing, this phenomenon. We were working on a very thin line of increasing the complexity of the hyperkähler codes. And I was being very careful about it. Right? So actions like doubling the ranks, for me, are very violent. I lose control. Right? The modulized space it's there. I cannot deny it, but it's very hard to analyze. Right? So we have to walk a very thin line in getting moduli spaces which are under control. And surprisingly enough, you also find them in completely unrelated problems. Right? So the question is, how far can we take this problem? More generally, if I give you a general, very generic gauge theory with many factors, and possibly a collection of Chern-Simons levels, send all gauge coupling to infinity, I want to know how to construct the Higgs sponge. This is still an open problem. Sometimes those 5D theories will have no Lagrangian descriptions, like these ones. So again, how do you figure out what is the Higgs sponge at infinite coupling? And how do you analyze the physics of instanton operators? So this is one question. So we got some step towards this direction. The next question is about the whole story of hyperkähler cones. Can we study hyperkähler cones as generic singularities? Those are normalized spaces which certainly appear in string theory and in gauge theory. And we would really like to have some guiding principles of how to think about special families of them. Thank you. Yes.
So in that situation that you have, like Coulomb Ramsler package situation at infinite coupling, now I can apply on the left-hand side 3D mirror symmetry. And I can write down that equation. Yes.
Yes.
And I can write down the left-hand side as X prime of some curve, which is much simpler because it will have a single equation.
No, the expression of that thing is some, the 3D mirror of that thing is some class S theory reduced to 3 dimensions. Some nasty thing.
It's not.
Well, not nasty. I mean, I like it, but.
Oh, it's a 2
Yeah, it's not the Lagrangian thing.
Okay. But 2 is a gauge.
Sorry?
The 2 is a gauge.
The 2 is the other 2 is on the line.
The one that's
Inbound.
no, the one that's at the top.
This one?
Yeah.
Yes. This, I should really think of it as a U2 gauge theory, in addition to all the
Because
rest.
these are, two TU and it's kind of fixed together. If that 2 were.
Well, I mean,
Yeah,
this is the 3D mirror of some particular, interacting non-Lagrangian SCFT of class S.
No, I know.
Reduced to 3 dimensions. So,
but it's very close related to things that you know, which are like, if you engage that 2 somehow, and you get, that in your quiver with 2 fundamental anchors. Okay, then that's a very well-known theory in terms of the TU, and some has a well-understood 3D mirror, which is just a single, probably a UN or an SUN with some flavor.
sure, but.
Very similar to what you have.
Well, except that ungauging that too is what Ami would call a violent action.
Well, ungauging these two will make the mirror a known theory,
Right.
which is very close to here. But we don't understand, that's so, this ungauged two, I really agree with Jacques here. This is really a violent action. We just don't understand what is this action of engaging.
On the 5D side?
As it acts on the model space. When it acts on the model space, it's very, I mean, we may try to put it as a challenge to understand it, but at the moment, certainly I don't have a good understanding of what it means. Yes?
I'm a little bit confused. So because of the dimension of the modular space, I thought we are talking about a single instant modular space. But now we are showing that.
You are talking about it. I never mentioned that single instant.
Because of the dimension of
No, you said doubling the rank was closely related to 2 instances.
2 instances. Good. Yes. Okay. So what are you saying?
And my question is that your final result seems to show the flavor symmetry at infinite coupling, where all instantons can contribute. So what am I missing?
Oh, but this, when I say that this is an order space of instanton, it's not the same instanton operator. It's only because we are physicists which have very low imagination that we call completely different objects with the same name. Let's not confuse. An instanton operator 5D has nothing to do with a 4-dimensional instanton, a classical solution of an instanton for which this is a model space. Right? And, it's really different. Really different. Right? Right? So indeed, this is the modular space of 1D7 instantons when I think of a classical four-dimensional problem. And here, this five-dimensional theory has chiral operators in the chiral ring, which are called instanton operators. They have very little to do with these things. For one thing, if it's an instanton, it's an instanton of an SUN field. Right? And it has very different properties. So, yeah, maybe we should be more creative with names.
A very small question. So this 5D tier H2Z infinite coupling, they define performance theory?
Yes, a UV fixed point in 5D.
Like one external hand here, but just that nobody still try to bootstrap these performance theories.
There's been quite an effort. I mean, sorry?
Yeah, the 5D example I think is exactly the missing is what kind of missing point. Right?
Oh, I see. You were looking for some examples. So, you know, the study of 5D fixed point was began by Zyber in 1985, possibly.
I mean, from the point of view of the bootstrap, right?
Oh, I see.
Something
You're familiar with this, but maybe others are not.
Okay, sorry, yes.
I see. Okay. So that. Yeah, I'm not sure what to say. So let me just say that whenever I have such a gauge theory, there would be a natural object which has a mass 1 over g squared. Since I'm in 5 dimensions, 1 over g squared has dimensions of mass, and you would call it an instanton. When I set this value to infinity, it will become massless, and therefore the Higgs point will become larger, the global symmetry will become larger, and we are trying to quantify how will it become, and those are the quantitative answers to this question. I could talk basics of the 5D.
Is there a way, I mean, it seemed in each example, the additional generator, the one of spin 2, was the one of spin greater than 1.
Yes.
Right? What its spin was and how it transformed under the global symmetry seemed to be something you sort of had to figure out in a case-by-case sort of way. Is there some sort of systematic understanding? So we're talking about chiral rings which have one extra generator, spin greater than 1.
Yeah,
is there some systematics for, what?
I didn't write it, so I just realized that all of them have N over 2.
Spin N over 2, yes, sorry.
And, so this requires computation, and it is said that for a gauge theory of type SUN, or any gauge that the spin of the instanton operator will be the dual Coxeter number divided by
Okay.
right? So here I'm using this generic result and Folkstorm computation.
Okay.
This computation is in the literature, it has been done.
I see. Well, so one of the reasons I ask is, for instance, we produce a long list of class S theories with simple isometry groups, which happen to, for instance, all be exceptional. Right? And so you might ask whether those fit into this kind of story, but I don't quite have the same systematics because I don't have the 3D mirrors available to me to study the Coulomb branches. So I'd like to sort of abstract from this construction something a little bit more.
There is a classification of all minimally unbalanced rivers. We could just split them into one of those. So we take an E6.
Yeah, E6, G2, you name it.
They have some homework to do, it seems. To compare and to try to figure. Yeah, hopefully there will be some nice cool finger for in the cases. Yet to be found. Yes. Thank you.